We're going to look at this video at rigid bodies, and in particular we're going to look at ladder problems. So this is where you've got a ladder resting against a wall. So have we look at the notes there, pause them if you want to read what's written there. We're going to look at a couple of situations. First of all, we're going to look here at if a ladder is resting against a smooth wall. You can see there is just a normal reaction. If it's a smooth wall, there's no friction. Had this not been a smooth wall, then friction would be acting in this direction here, and that would be to prevent the ladder sliding downwards. So there would be a friction here. I'm going to call it F1. Okay. Likewise, if the surface, the ground is smooth, then there's a normal reaction going up here. If the ground was rough, the ladder would move in this direction, which means friction has to act in this direction to prevent motion. Okay, to prevent the ladder sliding. So that's what you're going to have. Another strange wee situation here. You can imagine if we extend this wee diagram a wee bit, had that been just an edge, your ladder's rested against an edge there. So you imagine trying to climb up onto a roof or whatever you're doing. Your force is coming out perpendicular to your ladder because it's really as if that is a beam or a rod that is resting against. And then you've got your normal reaction going up here as well. Okay, let's have a look at a question. So this question says, a uniform ladder AB of mass 10 kilograms and length 4 meters rests with its upper end A against a smooth vertical wall, end B on a smooth horizontal ground. So there's smooth horizontal ground. A light horizontal string which has the end attached to B and the other end attached to the wall keeps the ladder in equilibrium. So that's what this thing is here. This is the tension in a string which is attached to B, pulling it in towards the wall. Keeps this ladder in equilibrium at an angle of 40 degrees to horizontal. The vertical plane containing a ladder and the string is at right angles to the wall. Find the tension T in the string and the normal reactions at the point A and B. And they have labelled this all for you. So let's do a couple of wee extra things we need to put on. So a bit like your planes, your inclined planes, that's going to be 40 degrees in here. And we'll do, and this is a hard bit that people find by, remember the old Z angles. If that angle was 40 in here, this angle is going to be in 40 in here, so that's going to be 40 degrees, and then we're good to go. I think we've got everything we need to do this. So to do these questions, there's only 3 things you can do, remember, same as in the previous videos. You can resolve vertically, you can resolve horizontally, and you can take moments. So resolving vertically, first of all, going up, you've got R, and going down, you've got 10G. So straight away, you can find out what your R is. So your R is 10 times 9.8, so it's going to be 98 newtons. Resolve horizontally, you've got your S then is going to be equal to T. Nothing we can do with that, unfortunately. And then a really good place to take moments about is this B, because that means this force here, R, which is acting through B, and this force T, which is acting through B, can be ignored. So we're going to take moments about B, and we're going to do clockwise equals anti-clockwise. Okay, so your clockwise moment, if you can imagine here, my clockwise moment would be this force which is going in this direction. That would be my clockwise moment. So that would be my clockwise would be that S. To pull that S round to that dashed line, it's going to be S sine 40. And its perpendicular distance is 4 away from B. And then the anti-clockwise moment, so I'll do a green colour here for this anti-clockwise moment, is going to be this one here. That's going to be my anti-clockwise moment. So that's going to be 10G cos 40, and that's times 2. And then a little bit of working out then, S is going to be equal to 10G cos 40 times 2 divided by, and I'll just write that as 4 sine 40. And then you can work out your S. Once you get your S, then you can get your T as well. So let me just work out what that is. My S then is equal to, works out to be, and I've done this already, that was going to be 58.4 newtons to 3 sig figs. Therefore, my T is going to be the same. It's going to be 58.4 newtons to 3 sig figs. Okay, next example. Next example we have got says bear with me a wee second. It says a ladder 5 meters long rests on rough ground against a smooth vertical wall, inclined at thigh to the vertical, such that sine thigh is 3/5. It has a mass of 20 kilograms and its center of gravity located 2 meters away from the lower end of the ladder. A man of mass 80 kilograms. Man of mass 80 kilograms stand on a ladder 3 meters away from the lower end. And what we've got to do is find, first of all, the frictional force on the ground, and we'll worry about the rest of it in a wee minute. Okay, first thing we need to do is do a half-decent diagram. So we've got that. You've got your A, you've got your B, you've got a normal reaction here, R2. You've got your normal reaction here, I'll call that R1. And the angle that this thing is acting at, is inclined at an angle of thigh to the vertical. Okay, so a bit different than this one. Thigh is in here, which means then your thigh is going to be in here. And then, what else are we going to have? We've got the center of gravity is located 2 meters away from the lower end. So 2 meters away, we're going to have to draw our vertical line going down. So that's our mass of your ladder, which is 20 G newtons. And we've got a man of mass 80 kilograms stands on a ladder 3 meters away. So it was 2 meters to get to here, sorry. 2 meters up to there, and then another 1 meter to get up to the next bit. And that's this man, and he was 80 kilograms, so 80 G newtons is his weight. And then this is a wee bit weird, and again, this is a strange question, very rarely are they asked this way, but if you imagine here, that was our thigh, that's also going to be thigh with that vertical, so the thigh is actually going in here, and in here, that's where that wee letter is Greek letter is going in for this case. Right, what was the total length of this ladder? It was 5 meters long, so that's going to be 2 meters for this bit, so we've got every dimension we need. I would also mark this in here, and this is tricky then, just to show you how we get this. This angle here would be 90 minus thigh, so then this angle in here is also going to be, I'll do it in blue, it's the one we want. It's also going to be thigh as well. So we've got all of those ones. We are ready to go. Right. It also tells you, if you ever get a question where it tells you in this form here, bear with me a wee second, if it tells you that sine of whatever the angle is equal to, what was it? Where on earth was it? It was 3/5. You don't actually work out the angle. What you would do is draw a wee right angle triangle. And sine, there's your thigh. Sine is 3/5, and that's going to be 4. And that's going to be cos of thigh is equal to 4/5. And then that is then you ready to go. Okay, now all you can do is you can resolve vertically, resolve horizontally, and that's it. Oh, forgot to put on my frictional force. There's my frictional force F here. Frictional force going there. So find a frictional force on the ground. Okay, let's get cracking on this and see what we're going to do. So we will resolve vertically first of all. You're going to get going up. You've got your R2, and it's going to be equal to 100 G. So R2 is going to be equal to 980 newtons. Okay. Resolve horizontally. R1 is equal to F, and then we go from there. Right. So how on earth do we find our missing forces then? We're going to have to take moments, and again we're going to take moments about this point, and quite often that is the case. The one that has got two forces around it, coming out of it, you take moments about that point. It makes life so much easier. So we're going to take moments about B, and we're going to do clockwise equal to your anti-clockwise. So I'm trying to keep this diagram on the screen so we can see it. So take moments about B clockwise. The only clockwise force you're going to have is this one here. So clockwise, you're going to have this force here pulled in this direction. So that is going to be, clockwise is going to be R1 cos phi, which we now know the value of cos phi. And then that is, how far away is it? It is 5 meters away. That's only clockwise force. The two anti-clockwise forces then, you've got, I'll do these in this red colour. You've got this one, first of all. I'll do it one at a time here, so bear with me a second. So that would have been 20g sine phi, and that's times 2. And then the other one, I'll do it in this horrible yellow colour. Nope. You're going to have this one here. So that is going to be 80g sine phi, and then that's times 3. I don't know why my pen has changed here, but it has. Okay, right. So if we work with that then, we've got all those values, so we just want to put all those things in. So 4 over 5, cos phi, remember, was 4 over 5. So that's going to be R1 times 4 over 5 times 5. That's just going to be 4 times R1. And then is equal to, and then over here, we've got our 20g. If you do all that, that's going to work out to be 20 times 9.8 times our 3 over 5 times 2 plus 80 times 9.8 times 3 over 5 times 3. If you work that out, you will get 1646.4. Divide across by your 4, you get R1 is 411.6 newtons. And your F then, remember, is the same as R1, so F is 411.6 newtons. Okay. Next part of this question then. Next part of this question says the least possible value of the coefficient of friction between the ladder and the ground. Okay, so I've run out of space here, but sure. So for part B, we want to say then coefficient of friction is least if friction is acting at its max, and what that means, i.e. it's acting, F is equal to mu r. Okay, so that means in this case, i.e. your F that you've just worked out, your F max was equal to whatever you've just worked out, 411.6. So that means 411.6 is equal to my R2, which I worked out, which was 980. So that's mu times 980. And then you can work out, then your mu works out to be 21 over 50, which is 0.42. Okay. Now part C, it says find the magnitude and direction of the resultant reaction at the ground. Okay, so that is this bit here we're looking at. So we're going to have to find the magnitude and direction. So you've got your, at B, you've got a force going up of 980, remember, and a force going left of 411.6. So we've got to find the magnitude and direction of this, this force. So let's just draw a diagram. So this is at B. You had your force going left, which was 411.6 newtons. Your force going up, which was 980. And you want to find out what the resultant force is and the angle that it's acting. So it's just Pythagoras. So R is going to be equal to 411.6 squared plus 980 squared and the square root. So R works out to be 1062.9 newtons to 1 decimal place. And then tan theta is equal to 980 over 411.6. Therefore, theta is equal to 67.2 degrees to 1 decimal place. Okay, and I would just make a wee note that that is above the horizontal. Okay. Right, excellent. That's another wee example done. That clearly didn't get it on the space. That's because this thing is zooming all over the place. Right, the last one then is, last type of example we're going to look at is when somebody is climbing up a ladder. So, whether or not it is safe to ascend to the top of the ladder will depend upon the magnitude of the frictional force which acts at the foot of the ladder. If a ladder is found to be in limiting equilibrium, that means it's on the point of slipping, basically. So when a person is part of the way up the ladder, then if they ascend any further, then the ladder will slip. To determine how far a ladder may be ascended, consider a situation when a climber is at a distance x up the ladder, and the ladder is in limiting equilibrium. Okay, a little diagram needed for this one. I don't think I've got very much space to do this one again. Okay, so we have got a diagram for this one here. It says a uniform ladder of mass 30 and length 5 rests against a smooth vertical wall with its lower end on a rough ground with coefficient friction 2/5. The ladder is inclined at 6 degrees horizontal. Find how far a man of mass 80 can ascend the ladder without it slipping. So here we draw our ladder. I should have drawn these out earlier. There's my point A at the top, my B at the bottom. Right, now notice here, instead of calling it friction, I've called it mu r because it's acting at its maximum already. It's a uniform ladder, so its mass, which was 30 kilograms, is acting vertically down. That's 60 degrees. At 60 degrees, that's 60 degrees. You've also got the man. I'm going to imagine the man has gone past the middle point. He may not have gone that far, but I'm going to guess that he has. The mathematics will work it out for us if he has or not. We will figure that out. The distance here, it was 2.5 meters to the center. It was x meters here, and that's your normal reaction R. I'm going to call this one going horizontally, I'm going to call this S. And that also, this angle in here would be 60 as well. Okay, so that's an S, not a 5. Okay, that's what we've got. We've also got mu is equal to 0.4. Okay, right, so the mu R, I haven't written it in here, but the mu R is, the friction error is mu R as it's acting at its maximum. So, the only thing we can do, remember, we can resolve vertically. Resolving vertically, you're going to get R is equal to, if this thing will let me write, R is equal to 110 G. So, R is equal to 107 0.8 newtons. Okay, your S then is equal to the mu r. So S, we can get S straight away. S is going to be equal to 0.4 times the 107.8. S then works out to be that should have been, apologies, that wasn't 107.8, it was 107.8, just it was 107.8. So then my S is 431.2 newtons. Okay, and the only other thing we've got to do then is take moments, and again we're going to take moments about B. Clockwise equal to anti-clockwise. I'm squeezing this in, apologies. So clockwise, what we've got going clockwise is this. What we've got going clockwise is this, and that's going to be then 5 times S times sine of 60. Anti-clockwise then, we have got anti-clockwise then, we have got this. And we have got this. Okay, so anti-clockwise, let's write down the X one first. It was 80G. 80G, and it's going to be cos 60 times X. And then also we've got 30G, and it's cos 60 again, but it was 2.5 away. Okay, I would do this, most of this in my calculator. We know our S, I should have written in my S there as well. Right, so I would do most of this in my calculator. Let me just write that all down again. I'll write that down over here if I run out of space. So instead of the S, I'm going to write what S was. S was 431.2, and then that was times sine of 60 is equal to 80G times my cos of 60 times X plus 30G times cos of 60 times 2.5. Okay, so we can tidy this up. It's a bit of a mess here, but you can do this. You use your calculator here. Your calculator can do this all. So do 5 times 431.2 times sine 60. We'd bring the 30 G cos 60 times 2.5, bring it across, and then that whole thing divides by 80G cos of 60, and that will give me my X. So you can get your X then, and your X is 3.83, and that's going to be meters to 3 sig figs. Okay, and that's it done. So you can see, didn't get that squeezed on and give myself enough space, but you can see really what we are doing there. Okay, right, last one for us to do. Says a uniform ladder rests in limiting equilibrium with its top end against a rough wall and its lower end against rough horizontal floor. Okay, great. So we've got friction on both. If the coefficient of friction at the top and the foot of the ladder are both 2/3 and 1/4 respectively, draw a force diagram and hence find the angle which the ladder makes with the floor. Now it gives us a wee clue. It says let the ladder be 2W and the weight be 2L, and the weight be W. And we'll go from there. Right, it's in limiting equilibrium so as well, so we've got our frictions acting at max for both. It'll be a decent diagram, and I'll scoot on beneath this if needs be. Right, what we've got first of all, I'll do a dash line up here. Here, I'll make it a wee bit smaller. Right, I've got my friction up at the top, if that's my end A. I've got 2/3 R2, where this is R2 coming out horizontally. We dash line here. I've also got very bad ladder there. It's not very straight at all, that ladder. Wouldn't like to climb it. I've also got my angle, which is theta, which we don't know. We've got the weight of this ladder, which we call W. That's theta. That is also theta. That is L. And that is L. And that is R1. And going this way, that is 1/4 R1. Right, okay, so what all we can do here, we can resolve vertically, we can resolve horizontally, we can take moments. So we're going to resolve vertically first of all. And it's going to be a bit of a mess here, this one, I'd say. Going to feel like it. So let's just get cracking, and we're going to resolve vertically. So resolving vertically, you're going to have R1 is going up. What else is going up? We've got 2/3 R2, and that equals W. So no help to us, really. We'll call that equation 1. We will definitely be coming back to that. We're going to resolve horizontally, and you're going to get that your R2 is equal to 1/4 R1. That's all you've got. I'll call that, I'll put that back in, I'll say put that back into the first equation. Therefore, I could say that is going to be R1 plus, then it's 2/3 times 1/4 R1 will be equal to W. And just do that in your calculator, do 1 plus 2/3 times 1/4. And what you're going to get is 7/6. So 7/6 times R1 is equal to W. Okay, and the same idea then, that means, or you could also say your W then is equal to, you can convert that into R2s then. So if we, how do we do that? Sorry, how do we do that? We want to get that into R2s as well. We know that R2 is equal to 1/2 R1. So that means R1 is the same as 4 R2, or sorry, 1/4 R1. So R1 is equal to 4 R2. So you're going to say then it is equal to 7/6 times 4 R2. So W is as well could be equal to, and that is just going to be 14/3 R2. Okay, so we've got quite a bit already. We can work all of these things out, and we're gonna take moments about the B to do this. So to do this and take moments about the B, here's our point B down here. We're going to just take moments about B, and again clockwise equals anti-clockwise. So clockwise we have got in green, we have got this going this way. So what we have got then going clockwise, we have got 2L, and that 2L is multiplying, and this is where the tricky bit is. 2L is multiplying both the R2 sine theta, and it is also multiplying 2/3 R2 cos theta. Now where that comes from, if you imagine this angle in here would be 90 minus theta, this angle in here would also be theta, so that's a tricky one there. So you've got to pull it round to that dashed line as well. So that's very tricky. So that's what you've got. And then anti-clockwise then, your anti-clockwise one's a little bit easier. You've only got one in actual fact, and it's this one. So anti-clockwise is just W cos theta, W cos theta times L, and then we're going to go from here. So we'll do a wee bit of cancelling out first before we do anything else. So that's going to be 2 R2 sine theta plus 4 over 3 R2 cos theta is equal to W cos theta. And then what we would be best to do here is to write your W in terms of R2. So we're going to write that again as 2 R2 sine theta plus 4 over 3 R2 cos theta is equal to then 14 over 3 R2 cos theta. Right, now what we're going to do is we can get rid of the R2s as well, and we're going to also, so we'll just cancel out the R2s, so you can imagine they're all just going. And then what we're also going to do is we're going to group all of the cos's on one side. So I'm going to leave I'm going to leave my 2 sine theta on the left. So I'm going to leave my 2 sine theta on the left. And on the right, I've got my 14 over 3 cos theta, then minus 4 over 3 cos theta. So I've got 2 sine theta is equal to just 10 over 3 cos theta, which then means you're going to have 2 divided by 10 over 3. Oops, done that the wrong way around. We want to get sine over cos, remember? So we want to bring the cos over to the left-hand side. So we get sine over cos, which is going to give us 10, which is going to 10 over 3 divided by 2, which means tan theta is equal to 5 over 3. And then do shift and tan of that, and you got 59.0 degrees to 3 sig figs. That is very, very difficult. So have we look at all of that? You would be able to get that fit onto your page. I couldn't, but you can see here our method: resolve vertically, resolve horizontally, and what that gave you then was a relationship between the R1 and R2, and then I gave you an ability to write your W in terms of R2. And then we could then do clockwise take moments by B, clockwise equals anti-clockwise. What happens is the L's cancel out first of all. We then convert our W to R2, and then we can cancel out our R2s and then bring all the sines to one side, all the cos's to one side. Remember, sine divided by cos gives you tan. And then we can get our angle then once we get there. That's all we had to do. All we had to do, he says. That was horrendous.